All right. I see the time is 4 o'clock from here. Good afternoon, good morning, good evening. Welcome to the Topology Optimization webinar. Today, the session is dedicated to data-driven multi-scale design. Following our new format, we will have a presentation of a review article or education paper, followed by presentations of 2 latest papers on the same topic. And this session is kindly organized by Professor Chen from Northwestern University in the US. Thank you for organizing the session today. Please take it from here.
Thank you, Jun. I'm going to share the screen, and we're going to allow just 1 to 2 minutes before everybody joins. Then we will start. Okay. So I'd like to first really thank the organizer of this webinar. You have seen here, this is the 29th top webinar. I really thank both the June as well as Niles. They have been working relentlessly throughout, I think it's already 3-4 years. It has really helped to bring the community together and allow us to share state-of-the-art information. So it's my pleasure of leading this webinar called the Data-Driven Multiscale Design. So we're going to focus on this theme, starting with that I will give an overview of a recent review paper that's published in Advanced Materials. It is actually a group effort. My postdoc, Doksoo Lee, as well as Liwei Wang, they are also in this participation here. So if you have any questions, feel free to put in the chat box, and we're going to respond to your questions. And after my 20 minutes overview, we're going to go into a presentation given by Professor Dennis Kochmann from ETH Zurich. He is going to talk about a paper on inverse design using deep learning methods. And then after that, Mohammad Mirzaali from TU Delft, he is, I believe, a assistant professor there. He is going to also show methods of deep learning for inverse design for another 10 minutes. So those talks are relatively short, but we encourage you to read the papers afterwards. And at the end, we like to leave sufficient time for some discussion. So feel free to put your questions in the chat box. Okay, we're going to answer throughout this webinar, as well as at the end. You can also unmute yourself and raise any questions that you have. So I'm going to try to watch for the time here, my clock here, to make sure I stay on time. So I want to start, before I go into my overview paper, I want to start with some motivation about why multi-scale design is important. So here are some examples that we have been working on in our research, really kind of touch the challenges of we called heterogeneous material system, which introduce a lot of complexity into the design problem. Here's an example of designing turbine blade. Material scientists are really working on trying to put different microstructure at different locations to improve the performance. So here I listed some examples where the location you need fine grains, the location you need coarse grained, and single crystal structures. So in general, continuous material design is more desirable, or designing different composition is more desirable than using a single material everywhere. On the soft material side, we have seen soft robot in order to deform to this desired shape. You do want to put property in a way that heterogeneous cross over this structure. And the optimality really depends on this heterogeneity. I'm also giving another example in optical metamaterial design that heterogeneous structure, heterogeneous property are desirable. So in topology optimization field, the multi-scale design has been there for many years already. Here we're talking about, I'm using this butterfly as example to illustrate that multi-scale design could be a 2-step process, that you start with design the topology at the global scale level and maybe also the property distribution. And the second step, you focus on designing microstructure at each different location. But there's always a question about how do you assemble them together to make it meaningful. Of course, you can also say I designed this whole structure as one piece, right? But that is super difficult because we have seen literature in multi-scale topology optimization. We know that topology optimization probably works the best when you have one material cross over the whole structure. So there's heterogeneity will pose additional challenge. Also, material property could be very high dimensional. Here, I'm only giving an example of just a tensor matrix here, shows how much dimension could be involved in 2D and 3D structure. And when you think about it, the property can be time dependent. It could be even more higher dimension. And lastly, the problem we face is that we have such an enormous in-node design search space we have to walk through. And topology optimization, if it's gradient-based, it's always very sensitive to the starting solution that you have. There's some other challenges associated with multi-scale design. And first one I'm listing here is if you have a problem which is multi-physics, there's interaction between different scale level. When you assess the performance, it improves challenge. The trade-off between efficiency and flexibility, as you can see the diagram here, you can choose to have periodic representation. You can also have multi-domain, different kind of class of material. And finally, it could be also aperiodic. So when you move to more free-form representation, it becomes more challenging from the efficiency point of view. And finally, manufacturability is always an issue. We have to make sure those cells are compatible with each other and ease of manufacturing. So when we talk about data-driven design, I don't think there's a universal definition, but that's a definition from my research group, that we look at a building block concept, meaning that you can think about the Lego, right, have different kind of structure, and you assemble them together. But using data-driven approach, we want to study the structural property behavior of the unit cell ahead of time. We want to extract meaningful patterns from the data. And finally, we like to learn from the learned patterns. We want to simplify the multi-scale design process and make it more efficient. So the typical flow or steps that's involved in our approach of data-driven method. First, we start from unit cell data set generation. And secondly, we call the machine learning or model construction to understand the structural property relation. And finally, we work on system level assembly to make it a very complex system. So in this talk, I'm going to walk through 3 different modules that we present in this review paper. It is a paper that actually took us a year, maybe more than a year, to work as a team together. And we collected, I think, close to 330 papers in the references that you can look into. So there's a couple of unique aspects of a review paper compared to some other review paper you see in the field. Firstly, I've been working in design research for many years, so my perspective is a little more design-centered. We actually look at design issues in 3 different modules: data acquisition, unit cell design. Second one, actually machine learning and data-driven methods, we call using that for unit cell design. And finally, the multi-scale design. So we call them 1, 2, 3. And in our review paper, we try to emphasize the interconnection between them and also show the design perspective for each of them. And we also looked at some of the we call underexplored issues in other review paper. For example, what are some of the limitations of the current data sets reported by other papers? What are the cost-benefit trade-off involved in machine learning? The multiple strategies in multi-scale design, and homogenization assumption, which could be a limitation in some of the multi-scale methods. And finally, we want to present that the data-driven design had to be task-specific, meaning that when you have a different design scenario, and you may want to do it differently, including all the modules that I mentioned, starting from data acquisition. So for the rest of the presentation, I will walk through each of those modules and highlight some of the key messages that we want to share with you. So data acquisition starts from the question about what is the design representation you should use. So in this paper, we listed a few different ones, including parametric. It could be multi-class, class meaning different type of architecture, implicit function, methods like pixel, just simply pixel voxel based, parametric curve surfaces, as well as constructive solid geometry. I wouldn't say this is an exhaustive list, and you may see some other papers that use some other representation. But when we choose which representation we use, there's several different considerations. The first one is that we found that they fall into two major categories, which is deterministic versus stochastic. And some of those representation is class-free, encouraging free-form representation, and some of them are class-based. For example, lattice is a kind of class, right? And when we think about them, we're also looking at compactness versus expressivity when we think about the mathematical representation. And we found increasingly people learn from the nature, so this nature-inspired representation. Manufacturability is always a concern, right? And it's very important to make sure it's feasible. And finally, when we work on digital engineering, computational methods, we want to be able to reconstruct any of those very quickly. So reconstruct capability is another consideration. Representation doesn't just stop there. Data acquisition actually is a process to think about how do we grow this database to come up with property that is superior, that is what we want, right? So there's an operation manipulation that we can do with the existing geometry we see. A simple example is this lattice structure. You can change volume fraction, the thickness of those beams to make sure that they kind of cover a wide range. Another one we found very useful is called class blending. So we can actually use numerical methods, start from different classes, and we blend them and together to come up with new structure and architecture. Finally, perturbation method is very important if we want to go outside of the zoom that we are familiar with. So we talked about these different strategies in our paper, and there is interpolation, extrapolation, class-based, class-free, parametric versus free form. So there are many different strategies about how do we combine different representation to come up with better choices. When we think about the geometry, coming up with geometric representation, that's free, very much like a free computational activity to some extent. But the harder problem is how do we do property assessment? So another topic we talk about is how do we decide, how do we sample to do simulation? Could be very expensive. And we use the term called task-aware adaptive sampling. So imagine you can start with very large like a data size, like here we are using a data source we created by just topology optimization, assigning different targets for the target. And you can also say you grab some, geometry from the literature. So the task here is how do we decide where do we sample those architecture to get the property information? And here I show you an example that maybe the anisotropic behavior is more desirable, right? So we start with also tropic metamaterial data set. The question is, where are the geometry we should sample to get the property information? So in our research, we actually view this as a design problem. We could use adaptive learning, Bayesian optimization. We can assign different criteria. So in our work, we look at two different sets of criteria. One is called diversity. So diversity could be geometry, could be property. And the other set of criteria is quality. And that is based on the desirable property that we want or design criteria. So the animation shows you how do we push the sample to the boundary, in this case to the envelope, pretty much is the physical limitation. And this shows the distribution of the data. If we use random distribution, if we only use diversity, which is red color, and when we use both diversity and the quality, here the quality is measured by the anisotropic behavior or property, you can see that we are able to push the distribution of the property to the two ends rather than kind of centered on the middle. So this can be viewed as a design problem. And then lastly, in the data acquisition, we also have different visualization technique to help us to see what's the differences between the different data set, just like SB plot, SB chart plot, visualizing different differences between the different geometry. And there's a high dimensionality associated with both the property and the geometry. So many of the machine learning technique these days can be useful to help us to visualize them in reduced dimensionality, like principal component as well as t-SNE plot. So now with the data set that we have, high quality data set, we can use machine learning technique. And here is a diagram that based on close to 60 papers that we looked at, we classify them into what are the physics they touch. And so optical, acoustic, mechanical, thermal, and to what kind of machine learning methods they use. You can see that deep generative model has been gaining more ground these days. And also what kind of the optimization scheme. And I think the other two speakers will get into more of this topic. So I will be very brief here just to mention that there are machine learning techniques, doesn't require any iteration, can do inverse design right away by specifying the targets. We call them iteration free, but there are all some other machine learning technique. You do have to add optimizer in addition to the machine learning model to do we call iterative design optimization. So in general, the generative modeling is a very powerful method to unify the representation. You can start with data sets belong to truss or isosurfaces, but the generative model is able to create free form. Geometry can have smooth transition and cross over many different properties. And here is some of the results from my group's research, show you what kind of data you can generate, and you can also use them to do functional graded structure design at the system level. Now I'm going to talk about the last subject, which is the multi-scale strategy. So in our work, we looked at top-down and bottom-up. I mean, I want to mention that this is really an important subject because we think the most beneficial case for the research in this area is to combine topology optimization with data-driven method. Not only topology, not only data-driven. When we combine them together, it becomes more powerful. So when we do top-down approach, we actually use topology optimization, gradient optimization to first identify the optimal distribution of the property at each location. And then we retrieve our database of the unit cell, then we assemble them together. It's a tailoring process to make sure they are compatible. There are cases that top-down strategy is not feasible when you have very high dimensional property space. And in those cases, we have to use bottom-up method that we start from the data set, create machine learning model, feed them to the high-level optimization at the top scale level. And in this process, we need to ensure geometric property mapping, compatible, learning latent space, and at the end, also manufacturing feasibility. So I'm showing you here a couple of slides about just representative work. I don't have time to say, which work is from which group, but I want to point out that there are a few research subjects. For example, when we use a bottom-up approach, we won't be satisfied with this kind of representation, that kind of straight boxes, and we want them to have orientation at the end, right? So there are different oriented unit cell representation, but come with it is an issue about how do we make sure that they're compatible unit cell by unit cell. So there's a geometrical mapping issue that we need to show. We need to ensure the tailing is fully compatible. So there are different works that including conformable mapping, decomposition, dehomogenization approach, as well as sawtooth function that can achieve this kind of mapping. So you can see at the end, we can actually design, this is a dynamic kind of a problem that looking at dynamic frequency, you can see the structure design at the end can have different orientation at different unit cells. We also looked at different representation crossover lattice, or we call the field-based method and the lattice pixel-based method. So you can see here that you can start with multiple class of material like lattice. One aspect to consider is when you use this representation, you need to ensure that unit cell neighboring, they have to be compatible. There are other methods which are field-based, like the spring nodal structure, as well as here, this example I'm showing you here, also using spring nodal architecture, that it has both some mechanics advantage as well as some advantage from the manufacturing point of view, and also ensure we call the functional graded design. So there are many other consideration can goes into this representation. Top-down method, this is on the top is the work we published called, in my group, we published called the string cloaking, that we look at the different, first optimize the property at different location, then retrieve the database to make them they're fully compatible. On the other hand, we also have some other strategy, I will call them strategy, about how do you retrieve the database. And this one on the left-hand side, it is a purely a discrete selection from the data set. And we also seen here, this work I believe is from also Professor Dennis Kochmann's group on these inverse design methodology using a neural network method as a tandem neural network method can achieve different kind of constitutive relationship and also ensure graded transition. And finally, this is a work from Caltech on using random growth as a representation that not restricting to any pre-defined geometry. So there's still a lot of strategy that comes into the top-down method. So I want to summarize some takeaway messages. The first one, that what we find is in the paper that we collected, we find that there's still some disconnect between purely look at physics-based, like traditional topology optimization method versus data-driven approach. Some of the paper data-driven methods fully focus on machine learning, but kind of left out the physics-based part. So there's opportunity to foster a tighter integration of the two. And we also believe that data-driven method can play an important role in architectural design, and come with it is the research topic data acquisition and the quality. And finally, I would want to emphasize multiscale is a strategy. You can use single scale, but multiscale is a design strategy to manage the complexity. And when we use that, we have to think about design representation and the scale coupling issue. So there are many rich topics here. I also want to mention a couple other we call recommended review paper that it's worth looking into, that's looked at. Two papers from on the top is from Professor Sigmund's group on the use of this artificial neural network as well as multiscale structure, and Faiz Mohammad from MIT had a very good review paper on deep generative model engineering design very broadly, and Dennis Kochmann's group has another review paper, how do we do machine learning for solid mechanics problem? And finally, we have another one that look at deep learning for inverse design. So I'm for photonic, and a lot of photonic kind of problems, which is not very similar to the to some of the mechanical conventional architecture design problem I talk about here. And finally, I will leave these slides with you about a website we created, metamaterials.northwestern.edu, where you can upload your own data set. We already have some data set there. You can upload your own data set. You can visualize your data set. You can zooming in, looking at different points of design and identify the nearest neighbor based on the similarity metric we developed in our work. So I hope that you will be happy to explore these different resources. So with that, I'm going to switch the presentation to Professor Dennis Kochmann.
Thanks very much, Wei. And hello, everyone from my end. Thanks for including me here. So we've been working on the inverse design of metamaterials for a long time. And in recent years, for the past 5 or 6 years, we've been using machine learning data-driven approaches a lot. You've seen some of the work already highlighted by Wei. Thanks very much. And today I thought I'd show you something that looks a little bit like diffusion, like science fiction. It's called video denoising diffusion, and this is mainly the genius stroke of an excellent PhD student of mine, Jan-Hendrik Bastek. And I'll show you what this is. And so long story short, if we start with what we know, not in terms of topology optimization, many of us know, for example, DALL-E. It's an image generation program where you put in a prompt and you get beautiful images. For example, if you type in, you want a photo of an engineering professor solving a hard problem, you get something like this. The catch here is that this is based on video denoising diffusion, meaning that these are AI-generated images that are not real. This is not looking up engineering professors on Google. This is generating images of people that don't exist. And this was DALL-E back in 2023, so about a year ago. And this is accelerating extremely fast. This is an example that was published just a few weeks back on Sora from OpenAI. And this is now the same for videos. I'll show you in a second. You type in a prompt and you say several giant woolly mammoths, going through a snowy meadow with mountains in the back and whatnot. And what comes out is this. And this is not Pixar animated videos. This is video denoising diffusion, meaning you put in a prompt and out comes a video, a photorealistic video in this case. You can try many other things. This is an example where the prompt was a drone camera circling, over a beautiful historic church built on a rocky mountain on the Amalfi Coast. This coast and this scenery does not exist. This is video diffusion. It is pure science fiction based on a prompt that you enter. And if you pay attention to some of the details, I don't know how well it is visible on Zoom, but if you look at some of the details of people running, for example, you will notice that this is video created. There's a person that starts running over here, and after a few seconds, it just disappears into nowhere. Here it goes, and then the person disappears. So you can see there are flaws in there, but it's a realistic image or video in this case of what you would like to see. How this works, I'll show you just in a few seconds. We can discuss later if anyone's interested. This is based on a so-called forward and inverse diffusion process. You start with realistic images and you add Gaussian random noise to this until you finally reach a true Gaussian distribution. And this is the forward process, how you go from realistic images to pure noise. And then the problem, of course, the catch is we want to go backwards. And so what the model does is it learns this inverse process, this denoising process of starting again with Gaussian random noise and through going in reverse through a Markov chain, it wants to create an image. And the point is this is conditioned on a so-called prompt, which means you have a gazillion number of videos online. Each one of them comes with a prompt. There's a caption, there's a description. And you learn how, based on that prompt, you can go from pure noise back to a realistic image, or if you do a time resolved, you create a video. And this is exactly what video denoising diffusion models are. And this is being used now, for video creation, but the question that we asked and that Jan-Hendrik looked into is, can we use this for mechanics? Because so far, this has been just fun. This is science fiction. How can we use this for a mechanical problem? And here's the way that we came about this. So imagine that instead of putting text in as a prompt, you put in a stress strain curve. For example, we could discretize the strain in increments of whatever 1%, and we say these are the stress levels that we want. This is the structure, this is the response, the stress strain response that I want, for example, periodic metamaterial to satisfy. And what I want to come out of this is an image of the structure, or moreover, why don't we go the next step right away? We want a video. And this video shows us a structure that has that response. And the colors in that video show us, for example, the stress distribution or the displacement distribution. It's conceptually the same. You enter a prompt. In this case, it's even simpler. It's not language. What you put in are pairs of stresses and strains along a stress strain trajectory. And what you want to come out in the end is nothing else but an optimal structure. Of course, I'm skipping a lot of details, but we can think about this conceptually. If you have an actual video, you would have 3 channels. Red, green, and blue. And in our case, what we do is we override this. Red becomes displacement component 1, green becomes displacement component 2, and blue becomes the stress in the 2 direction, sigma 2 in this case. Then you have your encoded mechanics in the video. And we can also put in more physics. For example, if this is quasi-static compression, we know that the pixels in every row are not just random, but for example, all the sigma 2's must add up to the same value because, by quasi-static equilibrium, force at the top is the same as force at the bottom. Moreover, force per area must also match what you impose at a given strain level at the macroscopic scale. And so the question we're asking is, can you do this? Can you do this with video diffusion or video denoising diffusion? And to test this, we tried it out. Jan-Hendrik did. We had to create a lot of images, as Wei pointed out. Data is the key here. So we used Gaussian random fields to create all kinds of random structures. We first created random structures, cellular structures like this. In this case, orange is material and black is void. We mirrored it twice to come up with a two-fold symmetry, so we could apply periodic boundary conditions. And then we took all these structures, we subjected them to quasi-static compression in this case. We applied periodic boundary conditions on the sides and fixed them at the top and the bottom. This material is elastic plastic. We used a well-calibrated 3D printed elastomer in this case. We do take into account contact, and we take into account frictional contact, because if you go up to 25–30% compression, there can be significant contact and friction involved. And then what we did is we generated a large training set. In this case, we simulated 53,000 unique structures. For each of those, we used Abacus to generate a video. The video looks like this. In this case, discretized by 96 by 96 pixels. And for each of these structures, we have a unique stress strain curve. And these are the pairs of data that we have for training of this video diffusion model. And then I'll just show you how the outcome is of this. Here's an example where we simply said, okay, I want a stress strain curve that looks like the red dots. We deliberately picked difficult examples. The white curve over here is the closest match from the training set, just to give you an idea of what is closest in terms of the mean squared error. And we put the red dots into the diffusion model, and out comes a structure. And the model tells us that the stress strain curve looks like the green triangles. Not too bad. Then we, of course, took that structure, we put it into Abacus, and the FE reconstructed response is the blue line, so it's fairly close. And what you see on the right is the video diffusion model on the left. Our prediction on the right is the FEM, the ground truth, the real response. Now, of course, you may ask, why does it do so funny things? Where does this kink, for example, come from? And you can also see that the stresses at some point start to rise very much in certain regions. Now, these images don't tell you the full truth, because this is every pixel color-coded in the undeformed configuration. But because we have the displacement information encoded, what we can do is just deform the structures according to U1 and U2. And what you get is a response that looks like this. On the left is the video that comes out of the video diffusion model. On the right is the FEM ground truth. And you can nicely see that at about 15% strain, these points here and there come into contact, and this is where it stiffens again. And as a consequence, we have the stress concentrations here. So the model just spit this out for free. We get not only the structure that has the optimal response, but we also get the FEM simulation for free. Of course, keep in mind, this may bear error, so you may still have to make sure that the FEM response is correct. But just having this and seeing what happens is a nice feature. I'll show you one other example. This is stress strain curve we put in. We wanted to see some pronounced softening. We put in the red dots. It turns out there is actually a best match, the white line, that was fairly close in the training set, and we wanted to see what happens here. So we run the optimization, and again, you get a structure that is much more closely aligned with the target, in this case, the green triangles. And if we then simulate it with 5 elements, you get the blue curve, so it matches almost perfectly through all the red points that we gave it. What you see on the left is the video prediction, on the right is the FEM. And at the beginning, when we looked at this sample, we were completely confused, because what we always do is we measure the distance between these two videos, just comparing stresses and strains, and they look nothing alike. In fact, this told us that the error was on the order of hundreds of percent, simply because the colors look very different. But then when we went to the deformed configuration to actually put in how these structures deform, this is what you can see here, it all started to make sense. Because what happens here is you have a close to symmetric system, and the FEM shows us that the system will buckle to the right, whereas the video diffusion model shows us that the whole thing will buckle to the left. And so the stress strain response is the same in both cases. The stress resolved, the resolved stress distribution is very different, but in fact, this is physical. It's not an error. It just means that the model has somehow learned that once you go to the left, you have to keep buckling to the left, and there's no reason to do otherwise, because the physics tells you once you go one way, you have to keep going in that direction. Keep in mind, and this is important here, this is with contact, with buckling, with elastoplasticity, which is something that cannot easily be done in other optimization scenarios. And so because I know the clock is ticking and I only have 10 minutes here, which is running out in a few seconds, let me conclude. So what I try to show is that machine learning offers quite some interesting tools for the inverse optimization homogenization challenge. We can also use it for forward homogenization, but that would be a story for another day. This video denoising is interesting for generative modeling of nonlinear cellular solids. And again, keep in mind, we have plasticity, friction, and contact in there, which is a challenge for classical methods. We can discuss afterwards if you can do similar things with topology optimization, but I guarantee it's a very hard problem to solve. Of course, this can be extended to other material systems and other properties. Some of this is already underway in our lab. I just want to mention that video diffusion is just one fancy tool that we came across here. There are many other data-driven approaches that can be used for this inverse design. We previously also looked, for example, at truss networks, and I won't talk much about this because the next presentation will be about trusses. And of course, when you use trusses, there's no point in using pixels. So here we can, for example, work with graph networks. And we had a recent paper where we showed that you can also use variational autoencoders to, for example, predict structures that have a given nonlinear response, including buckling and plasticity also for trusses, but not using pixels, but using a graph representation. And maybe the last point is a bit of a consolidation. Is this going to replace topology optimization? No, by no way. You know, we had 96 by 96 pixels. We had to do a large training set. This prediction is limited to the trained load case, but it is a very interesting tool that offers you insight and can generate never seen or never tested structures that are very close to the response you want. And for example, now you could easily use these designs as the initial guess for your topology optimization, which does depend strongly on the initial guess. And so this is all I wanted to share. Sorry for being 30 seconds over time. I'll stop here and be happy to answer questions later. Thanks.
Thank you very much, Dennis. And we're going to move to the next speaker, which is Professor Mohammad Mirzaali.
Yes. Can you see my screen?
Yes, it's correct.
Yes. Yeah, thank you very much for the opportunity. I'm Mohammad Mirzaali. I'm assistant professor at the Department of Biomechanical Engineering at the TU Delft. My work and the work that we're doing in our group is focused on biomimetic tissue interface engineering. And before start of my talk on inverse design of stochastic 3D network systems, I would like to thank my team, in particular Helda and Mauricio, my former PhD candidate, who contributed significantly to this to what I'm going to present today. So what we do in our group is more focused on biomedical application, as we're coming from the Department of Biomechanical Engineering. In that respect, I want to start with some basic need and definition of why we are using machine learning for the design of these metamaterials, so to call. So mechanical metamaterials, we have the definition for it is engineered material that whose unusual properties come from their marker architectural design. And for the design of these mechanical metamaterials, we can focus on the geometry or on the material deposition at different length scale or at different spatial part of the lattice structure. But for now, I want to only focus on the role of geometry on the design of mechanical metamaterials and skip the material part. We have several publications on that, and I only focus on the role of geometry for now. So the geometry of mechanical metamaterials can be composed of either repeating unit cells or random network. And in particular, I want to focus only on one of these, one of the specific unusual properties of these metamaterials, which is auxeticity. And there are typical geometries that can create this auxetic behavior, and auxetic behavior means a negative Poisson ratio. So that means that when you have a combination and rational design of combination of these auxetic and non-auxetic structure, you basically are able to program the deformation, so to speak, and also to see how to basically come up with unusual deformation as you want. But then, as for the clinical implication, what we use metamaterial or so-called metabiomaterial is that we use these for the creation of hybrid meta implant, in which we combine auxetic and non-auxetic unit cell design with respect to the state of stress that is exposed to the bone and implant interface. And for that case, we hypothesize that such combination can create a better integration between the bone and implant. But in that case, what is important is the elastic properties of the implant, because what we want to have is basically, first of all, the elastic modulus of the implant should match those of bone. And second of all, it has to be also, the Poisson ratio has to be also tuned in such a way that we create a better integration between the bone and implant connection. So what we can get from this random network is that we can, as opposed to the repeating unit cell design, is that this random network can extend the design space that we have. And these designs are basically less reluctant or less dependent on the local defects in the metamaterials. And what also is interesting for us is to find out metamaterials with sort of unusual properties, in that case, double oxidicity, as we have in here. And this double oxidicity, as you can see, is super rare properties, which is in here like less than 2% probability ratio for these unique properties. So what we did in this paper was that we introduced physics-informed deep learning models that combines deep learning based forward predictor models with the generative models. Basically, what we did was that we started with a trust-based unit cell composed of 4x4 nodes, and then generated a very fast, effective computational models. So we were able to create millions and millions of simulation in a couple of hours, and then validated this model and extended the design space that we have in terms of the elastic properties in different directions, and then use this deep learning forward-based model basically to predict to train the microstructure that were composed of matrix of ones and zeros that shows where the trusses are or not, and then back and create and find out the related anisotropic elastic properties. And then in the second step, what we used was using this conditional variational autoencoder. We generated a unit cell generative model that composed of two parts. One was that we used these elastic properties and microarchitectural design and mapped them into a latent space, and then use this latent space for back calculation of the microarchitecture. And from this microarchitecture, we were able to back calculate the elastic properties. So basically, we were able to extend the design space that we had, and then also find out new properties that were not in this design library as was before. Another aspect is that when we're talking about the metamaterials, we are assuming that the metamaterial is an infinite number of unit cells, and then this infinite number of unit cells, and there's also another aspect that is about the printability of these structures, because the number of unit cells that we have is sort of dependent on the number of unit cells that we have. So we also bring the size agnostic feature to in our model. So basically, we not only have these material properties, microarchitecture, but also the dimension in X and Y, and then back calculate the elastic properties by this size agnostic model. So if I want to show you an example of how this looks like, so basically we are asking for certain elastic Poisson ratio, double axiaticity, for example. We are asking for certain mechanical properties. So our model is able to give, based on the requested dimension that we have, it provides a different range of microarchitecture at different sizes with respect to the basically machine design that we have. We can just fill in this unit cell design with different geometries. But what is also another feature of this machine is that of this model is that we not only have the ability to generate this unit cell model, but then so then for certain properties we have a couple of different types of design with different dimension, with different microarchitecture. But then what is important is that we have to also select the best candidate of this design that basically is fitting our properties. And that means that basically what we need to have is, what we also added to this system is that we also ask for the stress distribution in the structure, and this stress distribution also we find out a structure that is basically having more homogeneous stress distribution in the structure, and then is more durable basically, and is able to carry more load over the loading of this when this structure is under the loading. Yes, so and that's it. It was very short, but I hope that it was clear, and I would be happy to discuss it further with you guys.
Thank you very much for those speakers staying on time. I was a little bit behind the schedule, but we still have 15 minutes that we could entertain questions from the floor. So I see that 2 questions has been already addressed. One is the question, or just briefly summarize. One is a question is about when you have data spread across different material and structures, some are anisotropic and some are isotropic. How do you sample the data for this kind of disparate data set? So my postdoc, Doksoo Lee, who is the first author of the paper, responded that it is not the issue that you start with a data set which has very different type of geometry, and using proper utility metrics, you could actually identify what source data are more useful than the other, and you can concentrate on the classes, or maybe even blending some of the classes to create new data sets that are more useful. So I hope that question is answered fully, and I just want to ask the first person who raised this question, do you have anything you want to add on this? The second question is about to Professor Kochmann on the really the local effects and whether it's how it's accurately captured by the proposed approach. And Dennis has responded that indeed that we do need some safety checks, such as error estimation, convergence criteria, to ensure that the results match with the final elements, estimation, as well as that we call this some kind of sanity checks, right, to ensure the computational aspect of the model fully captures all the intricate details. On the other hand, I think in their research, they do found that there's only minor differences, including the stress distributions for the data set that they collected. So those are the 2 questions that I see kind of ahead of time before we started the Q&A. So let's move to, I think some of the questions probably have to addressed on the spot. When I'm looking through the question, Dennis, do you have anything you want to add to your response to the first question, the second question?
Not necessarily to those, but I see more questions from me popping up. So if you don't mind, I can also respond.
Why not? Why not? You just respond to read the questions and respond to them. Yeah.
Yeah, thank you. So there's one question, which is how well the method approach works for simpler stress strain curves, considering that we had quite exotic curves in there, and also why go all the way to videos instead of just predicting the structure. The latter is easy to respond. We actually tried using images only instead of videos, and it turns out that using images works great for linear properties. If, for example, you want to predict stiffness, anisotropic stiffness or whatnot. But if you want the full nonlinear response, then just learning images was not sufficient. Others had done this as well. But if you really want the full nonlinear response, you need a video. You need to learn from the video because the structure itself was not sufficient. And in terms of exotic curves versus simpler ones, it's true. If you look at the full data set, we had thousands of structures in there. Some were relatively boring. They looked like a Nehookian. Others looked like Muniriflin or whatnot. So this data set had a very rich response. And if you plot the full range of structures, you have the boring ones included in there. We also tried very simple things. For example, predict a structure that is 30% stiffer than the stiffest in the training set. And of course, then what happens is, it will try to put as much material in as it can. And by doing this, you end up with more boring structures. But everything we've tried, it worked relatively well, even though, you know, the training set was a bit exotic, if as you say.
And there's another question, for you.
Yes, the second one, which I haven't read yet. Your example that shows softening was interesting since you showed a structure that used buckling for the no exact. In fact, as soon as you showed the displacement load curve, immediately thought of a double cantilever beam. Yep, it was obviously it didn't account for this type of mechanics in the training. So I'm actually wondering what would happen if you had included it with them. So that's interesting. So the question basically is, if you have a particular structure included in the training set, would it be found? And the simple answer, I would say, is not necessarily, because one of the strengths of these generative models is that they're not lookup functions. They don't go to the training set and look for what is closest and then give you that. So in fact, these generative structures are based on generating structures that do not necessarily exist in the training set. And so if you include that particular mechanism, it might well be that, you know, the model is informed by that and then generates new designs. But there's no guarantee. In fact, I would almost bet that it does not reproduce that particular design from the training set if it gives a similar response, but generates something else that also produces that response. It's an interesting question.
Yeah, I'd like to respond to Jing Wu's question about, this is to all the speakers, how much knowledge of AI is needed for a master PhD student to work with it for solving engineering problem. Suppose the student has engineering background and AI is not part of the curriculum. I think Jing brings up a very important questions. Actually, kind of, this is something we as a faculty have been thinking about, is whether we should develop new curriculum that is engineering oriented or even design, mechanics oriented curriculum for AI, right? Because currently our students are taking AI courses mostly from computer science department. Actually, it becomes more and more difficult to get into those classes. You know, my students are put on the wait list. The wait list is the same size as the size of the class. So it really kind of encourage us to do more teaching from our own disciplines. My answer to this question is that AI is an evolving field. So as a new generation of researchers, you need to understand the basic principles. You need to know some of the major differences of the different methods, right? But to deep dive in the methods, which method you should do deep diving, it really depends on the nature of your research. Just generative modeling itself, we have seen different methods coming out. Each day there is hundreds of new machine learning paper published, right? So on one hand, we have to keep up with all this new development. On the other hand, I feel we most likely as a user pick and choose methods that are most useful for us. So we have to understand what are the kind of the features of different methods and why they will be truly useful for us. So that's my answer. As anything, Dennis and Mohammad, you want to add to this question?
No, I generally agree. One point I would like to make is, I think it's important that one comes with domain knowledge to this. I mean, machine learning is something that many students pick up later during the masters, if they're engineering students, or also, as you say, in integrative curricula nowadays. But one of the things that we shall not forget is that all of this is great, but you need to understand the mechanics and whatnot behind this very well. I think this is one of the key takeaway messages. That's also why I'm saying that, you know, topology optimization and mechanics and all this will not be obsolete. So it's the combination of the two that will lead to success.
Yeah, I fully agree with those notion, because I think we talk about deep learning could be very data hungry. And one way to resolve this issue is introduce physics-based modeling in the process, right? Another reason it's important is we have to understand what's the end goal. So without the domain knowledge, we're not clear, right, about what is the end goal. Anything else that Mohammad, you want to add to this conversation?
No, I fully agree with both of you. I think that's important in terms of practicality. Is also one feature that I want to add is because what we are focused on is on the medical devices, and I think AI is also finding its route to the design of medical devices, and I feel that particularly the new generation I feel a lack in the knowledge of fundamental science and the new generation. We have to try to cover that, of course.
Yeah. Going back to some of the technical details, I want to ask a question to Dennis about, for the machine learning model, you talk about how much data actually you need for the model that you created.
Yeah, so in our particular case, this was on the order of, if I go back to I had it on the slide, I think it was on the order of 53,007 unique samples is what we had in this particular case. So you need to have a relatively rich data set to do the learning.
Okay. And Mohammad, I have a question to you about, at first I would like to comment, I feel this random representation, sometimes it's helpful to help to create more designs, right? You know, there's a strategy. I want you to elaborate very briefly the scale agnostic. I didn't fully get that. Could you just kind of respond to this quickly? I do see there's another question coming up, so I hope we can entertain that question too.
Yeah. So imagine that you have a device and you want to fill that device with a certain number of units. You can have you know, 2 by 2 units to cover this device to this device that you have, or you can have more than that. So you can just increase as many as the units that you have to reach to the properties of the solid material, basically. This size agnostic feature tells you that it is you don't really need to think about the number of units that you have in each direction to fill into your design domain, basically. And also, and in addition to that, it is also important to think about the 3D printing methodology, because with the 3D printing, you have also a resolution problem that you cannot really go beyond certain sizes for the 3D printing. And that means that also the number of unit cells will be also limited by the resolution of the unit cell. So that also plays an important role to know how many unit cells at the end you can fit into certain design space that you have. And that feature tells you that, yeah, okay, so for a specific design space, you can do, we can reach to the same properties by this number of units. Also, you don't need to fill the whole space with as many as units basically that you have. I hope I was clear with my.
Yeah. Okay, great. I saw a question somehow on my screen. It kind of goes away. I think it's from Charlie Avilan about when do you use AI machine learning? When do you use topology optimization? I want to get my shot on this question. I feel if you have a single physics problem, if you know the a great, you know, guess for the initial solution, topology optimization is still very much applicable. But when you start a multi-physics problem, like assessing the behavior becomes important, and the solution space is a very like irregular, complex, like the heterogeneity I talk about, and the way you really can benefit from pre-training. I want to emphasize this, training lots of things offline, and then use it maybe for different tasks. Like if I have this new requirements coming, tell me quickly what's the solution, customize the solution, and you have some training ahead of time. Machine learning model could play important role, and also bridging some of the skills of passing information the lower scale to the high scale level. So that's my take on that question. Anything, Dennis and Mohammad, you want to help? Yeah.
If I may quickly add, so the one point I agree is speed, right? If you do topology optimization, it's slow. Many of these predictions we make are within a microsecond. And if you have to repeatedly ask for optimal designs, let's say you do a 2-scale or 3-scale or whatnot optimization, where you're optimizing at the macro scale, but at every point, you also have to find an optimal structure on the lower scale. This may not be computationally feasible if you do optimization on both scales simultaneously. But if you have a very efficient tool that tells you what is the optimal structure underneath, then you can use the topology optimization classically on the large scale, but use the data-driven approach for the small scale optimization just by speed. And the second point I want to make also to this and to another question that was being asked, what's nice about data-driven approaches like the ones we've seen is that they are statistical. If you do topology optimization, you get a deterministic response. If you start from the same initial guess, you're going to get the same structure, unless you perturb it somehow. when we asked for a certain design for a stress strain curve or for anisotropic stiffness, you can immediately get 2, 3, 5, 10 different designs that are as close as possible to that design. And then you can look at these 10 different designs that are close to what you want, and for example, implement secondary criteria that you may also care about, manufacturability or buckling strength or whatnot. And so I think one of the advantages of data-driven approaches is they generate many designs for the same prompt, for the same input. And this is something that comes out of statistical nature as opposed to deterministic FEM modeling.
Yeah, another case I think we can bridge is data-driven methods can create initial solution maybe to the problem, right? Good guess. And then we use topology optimization. I know there's people who are working on multi-physics topology optimization for many years. I'm not saying topology optimization cannot solve multi-physics problem, but it could be very sensitive sometimes to the starting solution. So data-driven methods can provide maybe some meaningful starting solutions. Anything else that I see? There's also questions answered already. Anything, Wang? I see you're there. Actually, all of my co-authors for the review paper are here, Wang Chen and also Yichin Chang. So if you have any questions, we have one. I think we're actually exceeding the time. So sorry, Wang. I hope your question has been answered.
Yes, it's been answered.
Okay, great. So I think then I'll just call it off here that we had a great session. I feel had a lot of discussion. We had to speak very fast. Sorry about that. But I hope the presentations are useful. And you can watch the videos afterwards, I believe. Yeah, from the top webinar website.
Yeah, thank you for a great session. So on 23rd of April, we will continue discussion on multiscale topology optimization, and that will be more on the traditional or more gradient-based numerical approach. So hope to see many of you